Hello, my name is Nathaniel Weir. I'm a PhD student at Johns Hopkins University, and this is my work with Adam Polyak and my advisor Benjamin Van Dermy on probing neural language models for human tacit assumptions. We start with an example on a subway. Imagine we have two people, Alice and Bob, who do not know each other but strike up a conversation while riding. At some point, Alice says to Bob, "I'm late for work. Henry got caught up sniffing a bird on 34th. Now, assume Alice has not previously mentioned anything about a Henry, or that she is late, or mentioned anything about her possibly owning a dog or having given him a walk. Nevertheless, Bob is able to infer from her statement alone that she is late because she had to walk her dog, who held her up because he got particularly interested in a dead bird. So how is this possible? Why is Alice able to say what she said, and safely assume that even from a concise statement, Bob, a total stranger, will understand what she means? We could imagine in an alternate universe that Alice might have to list all of these auxiliary pieces of information that are necessary for proper inference of the meaning. I'm a person, and people can have dogs, and dogs need to be walked, etc. So to explain this phenomenon, we turn to a work in the 1970s by the linguist Ellen Prince, in which she proposes to formalize the roles that various forms of presupposition play in discourse. Prince defines the notion of a stereotypic tacit assumption, which can best be described as an NP-VP proposition, denoting a belief that we carry about categories of things, such as people or dogs, that do not have to be stated for someone, even a stranger, to assume that they are true. The role of the STA in discourse is that each individual holds a very large number of STAs coming into the conversation, such that they can be accessed and relied upon for both comprehension and pragmatic reasoning. What this means in the context of our example is that Bob is relying on his own STAs about people and dogs in order to fill in the gaps of the logical steps to arrive at Alice's intended meaning. On the flip side, Alice can rely upon the fact that STAs are commonly held among most people in order to prune the extraneous arguments from her statement. Even though Bob is a complete stranger, she can reliably assume that he will know that people have dogs and dogs need to be walked. We can therefore see how crucial a role STAs play as a form of common knowledge leveraged for the understanding and reasoning about language. As such, there is a long history of work in both linguistics and natural language processing on the quantification and formalization of these kinds of common knowledge. So given that these STAs are crucial for humans to understand language, they should be of great interest to AI and NLP practitioners who aim to build machines to achieve the same level of understanding. What we ask in this work is whether recent advances in artificial language understanding have made strides towards this very goal. We ask whether mentions of STAs pertaining to a particular concept invoke its recognition by an artificial agent, just as they do for humans. And vice versa, we ask if mentioning a concept itself will elicit a human-like recognition of its commonly held propositional assumptions. So in particular, we consider recent very popular neural language models, which learn to predict distributions over words given surrounding context. These models are trained using a task called masked language modeling, in which the model learns to predict words that have been masked out of a document. For example, a model might be given this Wikipedia snippet with a word masked out. They can see the surrounding words on either side of the mask, and it is their job to predict what are the most likely words that will appear in the slot. This task is done for upwards of terabytes worth of text documents, but all the model is ever really doing is receiving some document, at times the same document as before, but with different words removed, and it's just predicting what is called the co-occurrence likelihood of the word with its surrounding context. These kinds of models are of particular interest to us because they've become essentially off-the-shelf transfer learning tools for creating high-performing language understanding models. That is, simply teaching a model to perform masked language modeling on large text corpora, and then transferring the model to learning a new task such as question answering, leads to substantial improvement over nearly all previous approaches to solving those tasks. Our method of investigation is a closed-style word prediction task. In other words, we are taking a model trained to fill in the blank and having it do exactly that. But it is doing so on a sentence that specifically targets the ability to associate concepts with their STA sets. In this way, we are asking whether the ability to grasp the stereotypic tacit assumption is a byproduct of learning the masked language modeling task alone. That is, it is a type of understanding that will simply fall out of learning this other task applied to billions of text documents. The model is not being trained on a new task with any objective geared towards specifically doing concept retrieval. In our first experiment, we ask whether mentions of a set of STAs invoke the prediction of the associated concept. What this looks like is a prompt containing a sequence of simple STA statements concatenated together into a single compound verb phrase, where the noun subject, which is a concept, has been masked out. We claim that if the language model predicts that the given concept word has higher likelihood than all of the other words in its vocabulary, then it has effectively grasped the relationship between the concept word and its STA sets. We collect our STAs from the Center for Speech, Language, and Brain Semantic Feature Norm dataset. This was a study originally by McRae et al., with numerous follow-ups by Devereaux et al., among others, in which the humans were elicited for conceptual properties that were then aggregated to distinguish the pieces of common conceptual knowledge that are most ubiquitous among humans. This study quite literally just sat human subjects down in front of a concept word and just asked them to list all the conceptual properties that they associated with it. Responses were then aggregated and sorted by their relative production frequency out of 30 subjects. As such, we take the properties from this dataset that were most commonly produced by the subjects so as to evaluate for the models for the associations that are as highly ubiquitous among humans as possible. We construct our prompts in an iterative fashion. We start with the single most highly produced property of a concept, which is typically applicable to a number of possible concepts in the dataset. We then iteratively concatenate another STA onto the end of the prompt before reevaluating the model's predictions. Ideally, as more of these clues are appended, we are ruling out some previously applicable concepts until just the target concept remains. This lets us measure a gradient of performance that tests the efficiency by which a language model can narrow down a target concept given each new STA appended. We track both the increase in the assigned probability to a word and also the probability ordered rank of the concept word, which we track using a retrieval metric called mean reciprocal rank, which is just 1 over its probability ordered rank. We aggregate the performance according to how many properties were in the prompt, meaning we are asking how well a model will perform at concept retrieval when given, for example, 3 common STAs about any arbitrary concept in the dataset. Ideally, both the probability and mean reciprocal rank will approach their upper limit of 1 as we introduce more STA sets. We evaluate 2 recent masked language models called BERT and its more recent variant, Roberta. These models have identical architecture that comes in 2 architectural sizes, base or large. There are the few differences between BERT and Roberta are in slight tweaks to the way that they are trained on large text corpora. Roberta, which stands for Robustly Optimized BERT Approach, is notably trained on a more diverse set of text and shows to outperform BERT on most language understanding tasks, which can also be said of larger variants outperforming their base counterparts. It is therefore unsurprising in a sense that the Roberta large model would also perform much better at the task of concept retrieval. But as we can see from our plots, this is actually quite a substantial difference. Notably, we observed that Roberta large achieves a higher rank-based measure of retrieval when given just 4 STAs than any other variant can with 10. We also noticed that it assigns nearly twice the likelihood to the correct concept word than any BERT counterpart. From these results, we can conclude that a model that is trained with more diverse data, Roberta, and a model with more parameters, a large variant, will yield higher performance on our task. On the whole, though, we do find that each of the models that we evaluated was relatively to very successful at this task. We also note, though, that when a model makes a wrong prediction, it is generally at least grammatical and semantically sensible. More often than not, a mistake is simply the prediction of a word that misses one or more of the STA clues that were strung together, or it makes a prediction that, in fact, applies to a given set of STAs, but wasn't necessarily the one that we specifically targeted. We also ran a variant of this experiment where we isolated STAs only of particular categories. That is, we ran the identical procedure to the experiment, but used prompts that, for example, only contained, say, visual properties, as opposed to, say, functional or encyclopedic properties. We found that showing the model only visual STAs, as opposed to any of these other categories, led to substantially lower performance. This makes relatively intuitive sense, as other work has found that models such as those that we evaluate that only learn from textual data will do a worse job of grasping vision-based information. In our second experiment, rather than measure concept retrieval given STAs, we explored whether we can make headways in the opposite generative direction, whether we could get a language model to predict the STAs given a concept. When human subjects of this norming study were asked to verbalize their STAs, they were given a concept word in a drop-down menu of linking relation terms such as is or has. That naturally led to STA-like completions. In this experiment, we attempt to mimic this scenario, but in a word prediction task catered towards our masked language models. We construct prompts that match the concept relation word syntax and have the model fill in the final word of the statement. It is important to note in this experiment that there is an inherent discrepancy between the human elicitation and the word prediction variant, in that the humans knew what they were supposed to be doing. They were given a list of instructions for performing this task, and then given this interface that specifically asked what are the properties of some concept. The human was therefore cued into the fact that this was a study about conceptual associations, so they should only be listing those typical conceptual properties that were salient enough to write down. On the flip side, for the language model, there is only so much that you can do to inject cues into a fill-in-the-blank word prediction prompt, since the only cue that the language model ever receives is that there is some context of words on which it should condition the prediction of a fill-in word. The language model does not know anything a priori as a human might, let alone that the model should be listing only salient conceptual properties as opposed to any other word in its vocabulary. So we experimented with various ways to modify the word prediction prompt to somewhat mitigate this discrepancy in cues and better elicit property-like terms. And we found that the most effective way to do this was to prepend the phrase "everyone knows that" to imply that a completion should be something that is ubiquitously accepted by humans. So we found that in particular cases, there was a significant overlap between the human and model responses. However, we did find that the effectiveness of this protocol varied quite a bit by the relation phrase and the model. This graph shown here measures mean average precision, which is an information retrieval metric associated with precision over a large set of ranked candidates. As we see, there is a relatively stable ordering of Roberta Large, outperforming all of the other variants, but the order of the other variants varies by relation. Meanwhile, when we qualitatively analyzed the predictions, we found that some of the responses that were labeled incorrect were a product of the elicitation. We found that models made predictions that were verifiable by the humans, but had not been reported by the human subjects in the study, possibly, again, a result of the difference in elicitation cues. And we also found that models predicted completions of a different grammatical type that was also licensed by the syntax of the word prediction prompt. For example, they could predict present and past participles as opposed to the intent and nominative. We also did notice legitimately nonsensical responses, some of which seemed to reflect biases towards particular phrase completions, regardless of what the concept was. For example, some models predicted that nearly all concepts were made of wood. And finally, we note that the choice to prepend "everyone knows that" to the prompts has a very large impact on model performance at times. If we ablate the prefix, we observe very steep drop-off in model performance on one of the relations, but also an increase for another. And so to conclude this presentation, we return to the work of Prince that first introduced the notion of an STA. We took the STA list that she gave off of the top of her head in her work and ran them through our protocols for concept and property prediction using language models. And we found that our best language model very well captured exactly these examples. We also explored a set of STAs from a different source. In this case, a work in NLP that aggregated sets of concept attributes derived from people's most common internet search queries. And again, we found that our language model grasped these conceptual associations very well. In particular, there's a very high overlap between listed attributes when given the concept. And so in conclusion, we have found that neural language models show through word prediction alone to be able to grasp these simple STA sets through masked language model. These models are very effective at retrieving concepts given a string of their STAs. And we found that models that were trained on more diverse data and that had more parameters are generally performing better at this task. We also found that in the opposite direction, STAs can be elicited through the same word prediction method, but that this process was volatile and sensitive to context and syntax. And thank you, and now we have time for questions.